In this video, we will talk about the upper and lower bounds theorem. So this is kind of the last tool in our toolbox to completely factor a polynomial with real zeros. We've talked about the rational roots theorem, we've talked about Descartes' rule of signs, and this, in addition to those other two theorems/rules, will make it somewhat easy for us to factor large polynomials. So first we'll start with a little bit of motivation. We'll talk about the upper and lower bounds theorem, and then we'll do a quick example to show how the upper and lower bounds theorem works. So let's consider x to the fourth minus 2x cubed minus 9x squared plus 2x plus 8. So I want to start this analysis by using the rational roots theorem just to figure out what our likely real rational roots are. So we take the factors of the constant term over the factors of the leading coefficient. Factors of constant term over factors of leading coefficient, and these equals possible rational real roots. So the factors of the constant term, factors of 8 are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. The factors of 1 is just plus or minus 1, which means that our possible rational real roots are just these numbers here. So now we can test something. We could grab maybe positive 4, and by the remainder theorem, if we plug in 4 into the polynomial, whatever we get is the remainder. So we typically use this to help us find the factors, because if some number c is a zero of a polynomial p, then if we use the remainder theorem, we should get 0. In other words, if we take a factor, x minus c, or a linear polynomial, and divide that into a polynomial and get 0, then that factor, that linear polynomial, is indeed a factor of the polynomial. So p of 4, we do actually get 0. And you can convince yourself that this is the largest 0 of this polynomial, but I want to see what happens if we just try something larger than 4. So let's try maybe 5 and do synthetic division with 1, negative 2, negative 9, 2, and 8. So if you bring 1 down, then 5 times 1 is 5, 3, 15, 6, 30, 32, and then what's that? 150 plus 10 is 160, and 168. So what's interesting to note is that the signs don't change from term to term in the quotient of this synthetic division. And this actually tells us something. This is the upper and lower bounds theorem. Let p be a polynomial with real coefficients. If we divide p of x by x minus b, for b greater than 0, using synthetic division, and if the row that contains the quotient and remainder has no negative entry, then b is an upper bound for the real zeros of p. So just to flip back up, in this case, our bottom row, which contains the quotient, and then in red here, the remainder, all of those terms in the bottom row are positive. So 5 is an upper bound of the real roots of p. And what that means is that we can't have a real root greater than 5 for this polynomial. And similarly, if we divide p of x by x minus a for a less than 0 using synthetic division, and if the row that contains the quotient and remainder has entries that are alternately non-positive and non-negative, then a is a lower bound for the real zeros of p. In this case, 0 is considered positive or negative as required. So what this means is if in the bottom row we have a positive and then a negative or 0, and then a positive and then a negative and then a positive, the number that we divided into the polynomial p is a lower bound of the real zeros for p. So what this helps us do is it helps us eliminate a lot of possible rational real roots of p that we get from the rational roots theorem. sometimes we may end up with, 10, 12, 14 possible rational real roots, and using the upper and lower bound theorem helps us narrow that down. So now a quick example so you can see once again what to look for that meets the criteria for an upper and lower bound for the real zeros of P. So it says, show that all real zeros of the polynomial p of x equals x to the fourth minus 3x squared plus 2x minus 5 lie between -3 and 2. So let's start with x equals 2. So if we're expecting 2 to be an upper bound on the real zeros of P, then we should expect that the bottom row will all be positive. So we need a 1, a 0, -3, 2, and -5. So we drop 1 down, 2, 2, 4, 1, 2, 4, 8, and then 3. And then if we note, all of these are non-negative. In other words, they're all positive. So this implies that x equals 2 is an upper bound for the real zeros of P. Now we'll try -3. So again, we've got 1, 0, -3, 2, -5. So we drop 1 down, -3, -3, 9, that's 6, -18, -16, 48, and then 43. So now if we write in the sign, we've got a positive, a negative, a positive, a negative, and a positive. So since those signs change term to term in the bottom row, this implies that x equals -3 is a lower bound for the real zeros of P. So if we had, for example, in this particular polynomial, we would also have possible real zeros of plus or minus 5. So what this tells us is that both the positive and -5 that we get from the rational roots theorem will not work as a zero for this polynomial. It helps save us some effort when we're trying to factor completely a polynomial. In the next video, I will factor a 5th degree polynomial so you can see how to bring the rational roots theorem, Descartes' rule of signs, and the upper and lower bound theorem together.